Hello, welcome to RC Video Reviews. In today's video, we're going to cover some RC basics. These are things that I wish somebody told me when I first got into the hobby. We're going to start off talking about batteries. I'm going to cover a couple of concepts related to capacity and voltage to show you how to interpret labels and what you're seeing out there on the net when you're shopping for hardware for your model. We'll start with a real simple example, and that's a standard AA battery. Everybody has these, right? So I'm going to take this AA battery and I'm going to put a multimeter on here to show you what happens when we connect our lead to the positive and negative terminals on this battery. You can see I've got 1.611 volts, okay? So that's a single battery. This is what we call a 1S battery. It's just one cell. There's nothing in series with it. It's just one cell by itself. Now, if I take another battery and I take the positive lead and connect it to the negative lead, what I've done is I've put two batteries in series. And when we do that, what happens is the voltage becomes additive. So if both batteries have 1.6 volts, 1.6 here, 1.6 here, then I should get 3.2 volts on my meter. So I'll just connect my leads. And there you can see 3.2 volts on the meter. Now, what does that mean and why do we do it? We do that because voltage is the motive force behind power. And the higher the voltage, the more motive force you have, meaning the more power you can generate. So by putting batteries in series, we increase the motive force of the electrons supplying current to the load. There's another phrase you'll hear, and that's called parallel. And in parallel, what we're doing is we're connecting the positive leads and the negative leads. I'll try and show you what that looks like on the meter. If I connect the terminals on the top and the bottom of the battery, we should see only 1.6 volts on the voltmeter. So 1.6 volts when we connect the top and the bottom. And what that means is that we haven't increased the motive force, but we have increased the capacity. Because I'm using two batteries, my load can run approximately twice as long. It's not that clear cut depending on a lot of factors, but suffice it to say, by adding two cells in parallel, you increase the capacity or the run time, how long your device will run. Okay, so that's a very fundamental look at series and parallel connections. And the reason that's so important is because you're going to see that quite a bit in the hobby. So let's move on to bigger batteries. I've got three different flight packs on the desk now. These are all 6-cell batteries, but notice the markings. This one says 4,000, this one says 33, this one says 1550. Those numbers refer to milliamp hours or capacity, so they directly go to runtime. A 4,000 milliamp hour battery with all other things being equal will run longer than a 3,300 milliamp hour battery. And likewise, a 33 should run longer than a 1550. Now, in flight, there's going to be some guys that like to argue, and they'll say, well, but if you go from a 33 to a 4,000, you also increase weight. That means you increase drag, so you don't increase your run. The point of the matter is simple. The larger the milliamp hour capacity of the battery, the more runtime you have if everything else is equal. So if I were to put these two batteries under load on the bench, I would expect this one to run longer. Full stop. Now, if I plug my leads into this battery, you can see that I've got a voltage of 22.96. And when you divide that by 6 cells, if you take 22.96 divided by 6, you wind up with 3.8. 3.8 is the storage voltage for LiPo cells. That's where I store my batteries. So I have 6 cells running at 3.8 voltage in storage, and that means I see 22.96 on the meter. There's one other number I want to point out on these batteries, and that's the discharge rate. You'll notice that this one has a markings that says 40C, this one says 30C, and this one actually says 75C. You may not be able to read that, but that's what it says, 75C. The way you figure out the discharge rate of the battery is you look at this C rating. This one is marked 40C, so you take your decimal point and move it over 3 places. 1, 2, 3. That means my number is 4.0. 4.0 times 40C means this battery should be able to tolerate 160 amps of continuous discharge. On this battery, the discharge rate is 30C. If I move my decimal over 3 places, 1, 2, 3, that means my number is 3.3 times 30 is 99. That means this battery should be able to support 99 amps of continuous discharge. Again, there's going to be a lot of discussion on this. I'm not here to judge C ratings. I can tell you that they're often overinflated. The best thing you can do is test for yourself, and you find batteries that you rely on and that you trust for yourself. So very often these C ratings are overstated because within the industry, there is no agreement on exactly how it's measured. One company might measure the C rating a little bit different than another, and they often use these numbers to inflate the stats on the battery. All I can say is find a brand you trust, ask other people, and ask how their batteries hold up. I can tell you for me, I like the Liperiors. They seem to hold up pretty well. That covers the three primary measurements of these flight batteries that you need to understand. The first one is the voltage. Remember that voltage determines your motive force. So the higher the voltage, the more pressure behind the current feeding a load, okay? So higher voltage generally results in more power. The second number is the capacity that's measured in milliamp hours. Bigger numbers mean more capacity. And then the third one is your discharge rating or C rate. And the higher the C rating, generally, the higher the sustainable or constant discharge rate in amperage of the battery. Now that we understand batteries, we're going to take a look at chargers. With lithium polymer batteries, it's essential that every cell has the same voltage. And the reason for that is because we run them in series. And if you have a cell that's higher in voltage and another cell that's lower in voltage, what can happen during flight is the lower voltage cell could run out of juice faster. And that's bad because you could damage the cell and you certainly will lose power. So it's very important to keep all of your cells in a LiPo battery at the same voltage level. We call that balanced. That's why every modern LiPo battery has what we call a balance lead. The job of the balance lead is to provide individual cell voltage to the charger so the charger can make adjustments to the voltage level of an individual cell. Now, when it comes to chargers, there are a couple of different features you want to be aware of. Notice on this particular charger, there's an AC input and a DC input. And what that means is this charger can receive its power from an AC source or a DC source. Doesn't matter. On the bottom of this charger, it says dual smart charger, 15 amps by 2, AC 200 watts, DC 700 watts, USB-C 65 watts. Pretty important to understand what this means because it goes to the charge capabilities of this device. And what they're telling you is when you have two batteries charging at one time, this charger can supply up to 15 amps per channel. This particular charger is what's referred to as a dual channel charger. And what that means is you can plug in two batteries, a main lead and a balance lead on this side, and then a main lead and a balance lead on this side. That means the charger has the smarts inside to manage the battery charging on the left side and the right side individually. What this marking means is you've got 15 amps of current available per channel. So that means this port can provide 15 amps of current to a battery, and this port can provide 15 amps of current to the battery. Now, another number that's really critical is the wattage available on AC and DC. There's a really simple formula you really need to memorize if you get involved in the electric aspect of the hobby, and that's that volts times amps equals watts. And likewise, watts divided by amps equals volts, and watts divided by volts equals amps. So when you see this kind of marking on the charger that says 200 watts on AC, what they're telling you is that when you're plugged into the AC port and the AC port is your primary source of power, you only get 200 watts. So if you have a 6-cell battery, what that means is you've got 200 watts divided by 28 volts, and that means you can feed that battery up to 7 amps. Now, if you look at the DC side, you've got 700 watts. And what that means, if you take 700 watts and you divide it by 28 volts, you get 25 amps. So obviously on DC, you have the ability to deliver quite a bit more current to the output channels on this charger. And like this charger, this little M9 is also a balance charger. Notice how it's got the balance leads right here and the main connection right here on the left, but this is only a single channel charger. That means you can only charge one battery at a time unless you make provisions for parallel charging, which is a topic for another day. This charger is intended to charge one battery profile at a time. It cannot do dual discrete charge profiles. And then finally, this M6D is very similar to this M6DAC. It is a dual channel charger, so you've got two mains and two balance leads, and it provides up to 500 watts at 15 amps. So the M6D is a little bit lower on the power output at 500 watts compared to the M6DAC, which can deliver 700 watts. However, at 500 watts, that's still more than enough power to charge a 6-cell 5000 at the full 5 amp charge rate. Now we can connect the charge rate to the power delivery capabilities of the charger. So on this particular battery, it's a 6-cell 4000. That means I'm going to be charging at 4 amps. And at peak, the peak voltage per cell is 4.2. So if you take 4.2 and multiply that times 6 cells in a battery, that means at peak, I'll see 25.2 volts when this thing is fully charged. Remember, the peak voltage of a LiPo cell is 4.2 volts. Don't go higher than that. You can cause a fire or damage. 4.2 is your peak. I multiplied 4.2 times the number of cells in this pack. That gives me 25.2 volts at the peak. So 25.2 volts, and I want to charge at 4 amps. All I need to do is multiply 25.2 times 4, and I get 100 watts of power required. When I look at this charger, I see that I can deliver 15 amps, which is sufficient. I only need 4, and it can deliver 500 watts of power. I only need 100. So this charger would be effective for charging 2 6L4000s simultaneously on individual channels, no problem. It's very important to understand that math because you don't want to go out and spend your money on a charger that you're going to outgrow as soon as you get a 4-cell or 5-cell battery. If you're running a 3-cell battery, the power requirements just aren't that high. But as you start getting into higher voltage batteries like 4, 5, and 6S, you're really going to start to want to see a little bit of power coming out of your charger. So just keep that in mind when you make your purchase decisions. Speaking of power, the next thing we're going to discuss are motors. When I first got into the hobby, motors were a great mystery to me because the industry hasn't settled on a standard set of measurements. So, for example, if you look at this SK3 by Turnigy, it's got markings on the can that say 3542-800. This 3542 number is a reference to the measurements of the width and length of the motor. The problem is that some companies use the outside measurements, including the can and the body of the motor, to come up with this number, 3542. Other companies use the measurements of the stator internal or underneath this can for their measurements. So this one says 2814, 800 kV. So even though these motors are very close in size and probably make similar power, the one on the left looks like it's a much bigger motor because they use bigger numbers, 3542 versus 2814. The kV number on the side of the motor is a reference to how fast the motor will spin depending on the voltage. So the more voltage you apply, the faster the motor spins. The less voltage you apply, the slower the motor spins. kV is a constant, so you can say, well, if I have a 4-cell battery connected to this motor at 800 kV, I'll probably get about the same RPMs as I will on this one, which is also 800 kV. When I started this section, I told you I would give you a couple of pro tips that would help you with your motor selections. The first pro tip is to pay attention to the weight of the motor. So even though all these numbers can be all over the place in terms of size, the weight doesn't lie. So if I take this motor, the 2814-800, and set it on my scale, I see 120 grams, 118, 120 grams. If I take the same SK3 and put it on the scale, I see 158 grams. That's very close in size. So these two motors with the same kV output, 800 kV and 800 kV, with a very similar weight like that, they will produce very similar output. The other pro tip I'll give you is a link in the description to a chart that's put out by Cobra Motor Systems. They have a cross-reference chart that's just amazing. They don't put every brand name motor out there, that's impossible, but they do provide a cross-reference for several different motor manufacturers. So when you pull that chart down, you can find a motor that you're interested in and see what the alternatives are. I really like that chart because it's awesome at providing a cross-reference for motors made from different manufacturers or for different size measurements on the motor itself. In general, when it comes to motors, bigger motors produce more power and slower kV motors require more voltage. So as you go up in kV, you generally bring the voltage down. As you go down in kV, you generally bring the voltage up and swing a bigger prop. So bigger motors, taller, heavier motors obviously produce more power. Slower spinning motors take bigger props and much more voltage. Next, we're going to talk about radios. First up, we're going to talk about the difference between PWM and SBUS. You're going to hear this a ton, and when I first got started, this was so confusing to me, I had no idea what was going on. So a PWM receiver is basically a receiver that outputs an electrical signal on a set of pins. So you can see I've got a bunch of pins down here on the bottom, and usually when we set these up, we take our servo. So I've got a servo right here, and we connect the servo to these pins. So if you have 4 servos on your model, you'll connect 4 servos to these pins. That's simple. The receiver takes the input from the radio on the ground and translates that signal to what's called pulse width modulation. And that varies the width of the signal on the signal wire to cause this servo to move. That's a very traditional and legacy setup that we see all over the place. Now, SBUS is a completely different animal. While you can plug in an SBUS servo directly to an SBUS receiver, that's generally not how we do things. With SBUS, what we normally like to do is connect our SBUS signal lead to either a gyro or a flight computer. So a flight computer and a gyro both can interpret SBUS. In the case of this Hobby Eagle A3 Super 2, you see I've got that SBUS connection right there. What that means is that every channel from the ground radio is transmitted to the receiver, and the receiver sends it to the gyro over a single signal wire. You might say, well, what's the advantage of doing that? Well, if you use a standard PWM arrangement, this is what it would look like. So a standard PWM receiver has to send individual channels out on individual wires to the gyro, and then the gyro can do its work and then send the signal out to the servos. If you take a look at this configuration, this would be a traditional PWM with a gyro setup going out to a couple of servos. If you move over to an SBUS configuration, all you have is an SBUS receiver with a single wire connected to the gyro, and then the gyro will have the leads to the servos, and the gyro is inserted now in between the signal coming from the SBUS receiver and the servo output, and it can do its job of stabilization. This is why SBUS is still such a popular option, because you can just run one signal wire from your receiver into your gyro versus the PWM arrangement where you have to run multiple outputs into your gyro. Just for the record, I am aware that the Radiomaster R168 does support SBUS out. This is illustrative only. Some receivers don't support SBUS out, so you're forced to use PWM. The next thing we're going to talk about is receiver technology. This is another topic when I first got started that just drove me crazy because it's a hot mess and I had no idea what I was doing. What I do want to show you is the important element of pairing a receiver to a transmitter. In order for radio control to work, your transmitter and receiver need to speak the same language. Just like if you want to communicate with another human being, you both need to speak the same language. That's what protocols are. They're a language. Now, every protocol has different specifications. They all think they're the best for one reason or another. That's not the subject for today. I brought out these different receivers because they all have a different language. This L9R, for example, speaks L9. So if you want to use this one, you need a transmitter module that can speak FreeSky L9. This FreeSky S6R talks D16. D16 is nothing more than a protocol. Don't get wrapped up around what's D8, what's D6. Don't get wrapped up around that. You'll go nuts. Just understand that every time they incremented the protocol revision, that just added more features and functionalities. The main thing to understand is that D16 is the protocol for this receiver. The transmitter needs to also be able to talk D16. If they both talk D16, that means you can bind this transmitter with this receiver and they'll communicate over the air. Next up is this little orange receiver. This is also an integrated stabilizer, but this orange receiver uses the DSM protocol. So if you want to bind that to your radio, your transmitter has to understand and speak DSM. This D4R2 is a D8 protocol receiver, so your radio needs to support D8 in order to talk to this one. This R168 is like the S6R. This supports D16. And then finally, I've got an example of an Express LRS receiver. If you want to talk to an Express LRS receiver, you need a transmitter with an Express LRS capability. In my case, on this radio, I've got an external module that speaks Express LRS. So this module just plugs into my bay in the back, and then it sends the output out on this antenna, and it talks Express LRS to this receiver. The moral of the story for all of this is that you simply need to make sure that your transmitter and your receiver speak the same language. Now I'm going to give you the pro tip. If you're just getting into the hobby, take a very serious look at the Radiomaster TX16S with the 4-in-1 multi-protocol module. And the reason I say that is because that module is integrated with the radio and the software. And when you turn that module on, you get access to pretty much every mainstream protocol out there. You can use FlySky receivers. You can use DSM if you want. You get access to all the FreeSky protocols, including D16 and D8. So here's D16. If you want the D8 protocols, you can click on that and use D8. So the point is that the Radiomaster TX16S with a multi-protocol module can talk to all of these. And you may say, well, what's the point? Why do I care about that? Well, because when it comes down to things like availability and size, you may have different needs. You may say, well, I'm going to fly this one kind of long. I want to fly a mile away. You might want an L9R for that. You might say, it's just a basic airplane. All I need is a cheap receiver with 8 channels. There you go, 168, just a PWM receiver. You might decide you want stabilization and you want to use DSM so your buddy can pair with it on a Spectrum. There you go. You may decide you want a FreeSky internal stabilizer running D16. There you go. This radio speaks to all of that stuff. There aren't many other options out there outside the 4-in-1 community that can do that. This radio can talk to all of those receivers natively. And then if you want to add even more functionality by taking a look at Express LRS, it's a simple matter to take this module, an Express LRS module, stick it into the back of the radio, and now I have the ability to speak Express LRS as well. And there are other modules like Tracer and Ghost and TBS Crossfire that you can use too. So the TX16S, when it comes to speaking languages, this one is like the master interpreter. It understands a lot of different protocols. And for you as the consumer, that's the important piece, because now you can use any of these receivers you want. You're not locked into one single ecosystem. You can use any of these that you want to use. That's why I really like the Radiomaster TX16S, is because it can talk to all of this stuff. Most other radios on the market cannot do that. Next up, we're going to talk about battery eliminators. Before electric power became a viable option for flying RC planes with the advent of brushless motors and LiPo batteries, they used to use these little tiny flight packs, and they'd connect them to the receiver to provide voltage to the receiver and the servos so you could power your servos. Because when you're using an internal combustion engine, they don't generate electricity. So they used a battery or a flight pack to provide electricity for the receiver and the servos. Now, these days, with these big flight batteries, the question was raised, well, do we really still need these if we've got these great big batteries? The problem with that, of course, is that receivers and stabilizers and even servos a lot of times run on 5 volts. So you can't plug 25 volts into that receiver because you'll blow it up. So what they had to figure out how to do is provide voltage from this 25 volt flight pack at 5 volts for the receiver, stabilizer, and servos that might be in most planes. That's where the BEC comes in. In the case of an electronic speed controller with a BEC, what they've done is included a lead that provides 5 volt power output regardless of what you have plugged in on the input. So if I take a 3-cell battery, which is 12 volts, and plug that into this electronic speed controller with a BEC, I can safely take that lead and plug it into my receiver and not cause any issues with the receiver, because on the output, it's only 5 volts. That's why so many electronic speed controllers have an integrated battery eliminator circuit. It's so you can provide a clean 5 volts to your flight receiver and your servos based on voltage coming in from the flight pack or the main pack. BECs come in standalone formats as well. In this hand, I've got a Castle Creations 10 amp peak BEC that supports up to 6S in. And in this hand, I've got a little iFlight ESC that also supports 6S, and it provides 5 amps out. BECs like this can be used to provide power to anything on the plane, including your receiver, and they're especially useful if you have what's called an opto ESC. An opto ESC, and I have no idea where they came up with a name for that one, does not include a battery eliminator circuit. It only provides signal to the ESC. That's it. So an opto ESC, there is no voltage out for your receiver and your servos. In that case, you might need to use a BEC that you connect to the main leads of your battery somehow, and then the main leads provide voltage through the battery eliminator and then out to your receiver or servos or whatever you have. The big thing to understand about battery eliminators is understand what your load demand is going to be. So if you're flying a big airplane with big servos and a heavy load, you might need to look at something like a 10 or 20 amp BEC, or you might need to power those servos directly from a battery. If you have a lower power demand requirement, say a basic receiver, maybe some 17-gram servos, you can probably get away with a smaller 5 amp BEC, which is very common in most standard brushless electronic speed controllers. All right, let's wrap it up. Battery eliminators are there to alleviate the need of having a standalone battery to connect to your receiver and servos in the plane. And the way they work is we connect our flight battery to the electronic speed controller, and the speed controller has a little chip inside that governs this lead to be 5 volts out. 5 volts is not universal. Some electronic speed controllers allow you to adjust the BEC voltage up to 8 volts. So take a look at what you need, make sure you understand what your needs are, and make sure you feed the right voltage to your receiver and your servos on your model. That wraps up my video on RC Basics for Beginners. If you like the content, smash that like button, subscribe, and hit the bell so you know when new videos hit the channel. YouTube should be recommending another video for you right about now. That's all I've got for today. Take it easy and get out there and fly something.